Swayam Prabha. Digital India. Educated India.
In this class, we are going to study about the basics of noise and noise monitoring. As I told you earlier, in condition-based maintenance, we do vibration monitoring, we do motor current signature analysis, oil analysis, etc. Noise monitoring per se is not a technique to do CBM, but when a machinery develops a fault, it makes abnormal noise. So, noise becomes an indicator or an alarm to us, indicating that something is abnormal with this machine. So, in that sense, we will study about what noise is and how noise monitoring is done towards detecting such abnormal conditions. Well, to begin with, what is noise? Now, there are very synonymous terms in the sense of noise, sound, acoustics. Okay. Well, if I was to define sound, sound is something which we hear, which our ears receive, we hear, we get the sensation of hearing. Okay. Then what is noise? Noise, you can say is very loosely you can say is unwanted sound. They say music, what is music then? Music is a sound which you appreciate, noise is a sound which you do not appreciate. Okay. So, this is related to the sensation of hearing. And this is because of God's gift to us, a pair of ears. So, we get the sense of hearing, we hear any sound because we have our pair of ears. Okay. Sensation of hearing because of the ears, but it's a long way between the ears and the machines which we generate noise. So, what is this acoustics? So, acoustics is a technical term given to the field of engineering, where it deals with the generation, transmission and reception of sound. So, this is the definition of acoustics. It is a science which deals with the generation, transmission and reception of sound. Okay. Now, generation means basically talking about the source, transmission means about the media, because this sound is basically because of a transfer of energy. From a source to a receiver, and obviously this requires a path. Okay. There is a path which is connecting the source and the receiver, and this energy gets transferred. And then what is this path? As you will recall from your high school physics, the energy is transferred as waves. These waves require a medium or a media. This media can be solid, can be fluid, like in air, water, or steel, structure anything. So, depending on the media, depending on the density of the media, the two parameters which come into play in the propagation of this energy in terms of waves from a source to a receiver, the density of the media and speed of propagation in the media play an important role. Okay. Now, this acoustical wave or sound wave, there will be many ways by which it gets transferred. One is because this incidentally the sensation of hearing which you sense is because of a small pressure fluctuation. Because if you look at our eardrum, and I will just draw it as a membrane here, a thin membrane is our eardrum. Okay. So, when the pressure waves are incident on this membrane is going to have a small deflection. Okay. And to these membranes are attached many nerve go to the nerve cells, okay. And then this goes to the brain. So, because of this pressure fluctuation, small pressure fluctuation, this membrane will undergo a deformation or displacement, and this is sensed by the nerve cells attached to the eardrum, and then we get a sensation of hearing. But let us look into this pressure wave. For example, right now our eardrum, if you plot the time history of the pressure being incident on the eardrum, this is nothing but the atmospheric pressure, and this is about 1.0133 in 10 to the power 5 pascals. This is incident on our eardrum. So, this is a very high value of pressure our eardrum is being subjected to. On top of this pressure wave, if I do a perturbation of this, or this energy is being transmitted because of somebody speaking, because of a machinery making noise. So, there will be small fluctuations in sound pressures, and this is I denote by small p t. So, this is the dynamic component. So, the total pressure incident on our eardrum is P atmospheric plus P dynamic, I can say, and this small pressure is what is known as the acoustic pressure. This small pressure is responsible for generating the sensation of hearing to us. In fact, I will just give you a value here. Right now in this room when I am speaking, the atmospheric pressure is 1.0133 into 10 to the power 5 Pascal, which is incident on your eardrum, and because of my voice you may be experiencing order of about 0.5 to 1 Pascal. This could be your value of P t. Okay. So, you see the beauty of ear, or God has made our ear so sensitive that over a high pressure of 1.0133 10 to the power 5 pascals, even a small fluctuation of 1 Pascal can be sensed by our eardrum as a disturbance, as something which is being incident on our eardrum. You all must have felt, if you go up a high speed elevator, okay, or go up a mountain or go under the water while you are deep diving in the swimming pool, you will get a sensation of as if your eardrum are popping in or popping out. That is because of a difference of the pressure around the eardrum. So, your eardrum in some sense is very sensitive to this pressure differences, and on top of it a value of 1 Pascal is large enough to give you a sensation of hearing. Okay. Now, this is regarding the amplitude of the sound pressure level. Now, if I was coming back to the waves by which the sound gets transmitted from one place to another, you would have recalled in your high school physics that there are two types of longitudinal waves and transverse waves. Okay. If I was to draw a transverse wave, PT, so the direction of transmission is along this direction, okay, but the particles have a maxima and a minima perpendicular to the direction of propagation. This is the direction of propagation and this is perpendicular, and thus it is known as the transverse wave. So, this particle, every particle here is oscillating about its mean position. This is the mean position. Okay. So, these particles themselves do not move, but they transmit the energy to their successive particles, and in that you would have studied in the longitudinal waves. So, there is a speed of propagation of the wave front along this direction, and that is the speed of sound in the media, but the particles themselves oscillate with a different velocity. For example, if I write down the displacement P t as a sin omega t, I can find out, or if I write this as the displacement, some displacement x t a sin omega t, I can find out x dot t is nothing but a omega cosine omega t. Mind you, this is the particle velocity, and which is different from the speed of sound in the media. Speed of sound means the speed at which this wave front is moving, and this velocity means the velocity at which the particle is oscillating, which is perpendicular. Similarly, in the case of the longitudinal waves, you will have successive compressions and rarefactions. Okay. So, what happens because of this successive compression and rarefaction, there will be a increase in pressure, decrease in pressure, and thus the wave front is going. But here in the case of longitudinal wave, the particle motion is along the direction of the propagation of the wave front. Now, coming back to this sound pressure level or pressure which you hear P t. Now, this P t is a very small quantity, and our human ear can hear as low as 20 micropascals, that is 20 into 10 to the power minus 6 pascals, to as high as 1 to 2 pascals, 1 to 2 pascals. But if you see this scale is very large, 10 to the power minus 6 to 2 pascals, and that is why it is felt, or it was felt, that this sound pressure level or sound pressure need not be represented in a linear scale, but a logarithmic scale, wherein we define something known as sound pressure level as SPL as 20 log to the base 10 P, this is the small p by P reference, where P reference in air is 20 into 10 to the power minus 6 Pascal in air. In water it has a different value. So, when P is equal to 20 into 10 to the power minus 6 pascals, SPL would be 20 log 10 of 1, that will be 0 decibels. So, I have resolved 20 into 10 to the power minus 6 as 0 decibels, and if you will work out 1 Pascal could be as close to about 94 decibels. So, you see, by using the log scale, all I have done is reduce the numbers from 0 to 94 decibels. This is written as dB, stands for decibel, this capital B. So, small d capital B, decibel. Okay. So, SPL is the magnitude of the sound pressure level is given in decibel. Okay. Now, another important characteristics which you will see when we have this log scale, lot of properties of logarithmic addition, subtraction, etc., will apply here. For example, suppose I have a machine A which is making a sound pressure level of 90 decibel. I have another machine B which is making 90 decibel. So, when both the machines are there, both machines operating, the total level will not be an arithmetic average of 90 plus 90 by 2, it will be not 90 decibels, it will be not 94 decibels, it will be close to about 96 decibels. Because log of 2 to the base 10 is 0.3010 times 20 will be close to 6 decibel. So, adding two sound levels of the same sound pressure levels will be, the level will increase by 6 decibels. Okay. Now, this sound pressure level is, suppose I have a machinery here, this is generating. Now, how is this sound generated? Because this machine, there is a dynamics. So, these particles about the machines are going to have a vibration. Okay. So, the air molecules next to it are going to have a velocity, particle velocity which is close to the surface. Of course, that depends on the radiation efficiency, etc. So, once these particles are having an energy, they are now going to excite or radiate in all direction. Okay. But you will see this sound pressure level, suppose there was no obstructions, they would go down, they would go in one particular direction, all direction in fact, and imagine this to be a spherical source. So, they would radiate sound in all directions, but you will see this SPL is proportional to 1 by R. Distance from the source, okay, provided there are no reflections. Okay. That means, with every doubling of the distance from the source, the SPL will reduce by 6 decibel provided, this is very important, provided there are no reflections, and this no reflections means free field radiation. Okay. So, if I want to find out the sound pressure level radiated by every machine, I can always take them to an environment where there are no reflections and then measure at a fixed distance. Usually, the standard is about 1 meter from the source, you measure what the SPL is in decibel. The reason you will see later on in the field of acoustics is why they prefer this 1 meter is in SPL in the free field conditions, whatever is the SPL in decibel, in fact that same would be the sound power level, because the radius should be 1, so on. I will not go into the details of sound power and sound pressure level, but provided there are no reflections. Now, what do you mean by no reflections? So, how do you ensure that there are no reflections? So, we have to have certain boundary conditions. Suppose there is a room, if this was generating sound in every direction, we have to ensure that there are no reflections. So, such rooms or no echoes, or they are known as the anechoic chambers, wherein free field condition exists. There are special chambers wherein we do not have, like they have like wedges like this all around them. And these are actually acoustical wedges having a very high sound absorbing capacity is what I will say right now. So, any wave which goes in here gets reflected and gets trapped in this material, and so this is a free field condition. Okay. So, when we do the noise leveling of a product or want to find out the sound radiated by the machine, we usually test them in such anechoic chambers. Okay. In fact, people test vehicles in such chambers. Now, in fact, they can put a grating here and then they can drive in a vehicle, rev it up and measure the sound pressure level radiated by it. In fact, the same phenomena is used in acoustical, the electromagnetic absorption of radars, and such chambers are also there in the radar and communication centers, where then they test antennas as well. And opposite to anechoic chambers is what is known as reverberant chambers. Wherein the walls are very hard. So, there are lot of multiple reflections. I will not draw all these multiple reflections. And because of such multiple reflections, anywhere you measure the sound pressure level, there will be uniform SPL. Okay. And such chambers are used for acoustical testing, etc., but we will not discuss them in detail. It is just opposite to what anechoic chambers are. Now, coming back to our discussion on sound pressure level. So, we have just talked about the magnitude of the pressure, and human being or human ears can withstand not more than 90 decibel. In fact, it is recommended for more than 8 hours. In fact, in this room while I am talking in the studio, it is a very quiet studio. If the studio nobody was speaking, this level could be as low as 35 decibel in this recording studio, okay, the ambient noise level. Okay. Now, when somebody is speaking in a comfortable classroom, this could be about 60 dB in a classroom, studio, and when an aircraft takes off, this could be about 130 decibel. Exhaust. So, you can get a feel of the noise levels which I am talking about. Okay. Now, question is, you would have seen that noise or sound, they are waves. So, at any locations the sound waves would be adding up themselves. So, we will have a summation of waves like you saw the example when we have one machine giving 90 decibel, another machine giving 90 decibel, we have an overall decibel level of 96 decibels. For example, I was to monitor the sound radiated by a machine. Do I need to have another machine next to it running or no? Obviously, your answer would be everything else should be quiet. We should be only running the machine whose noise is to be measured. Now, you would have seen from this logarithm scale, if one machine C generated 80 decibel, machine D generated 70 decibel, and machine A generated 90 decibel, the presence of the machine A is so loud, that is 90 decibel, the presence of 70 would only raise it by 90 point, some small fractions, same is to about 80 decibels. Okay. So, the presence of a machine with a level 10 dB less or 10 dB less or more does not affect the machine. So, for example, if there is a 90 dB machine, 80 dB presence or a 70 dB presence is not going to affect the overall value of this 90 dB. But if there is 90 and 90, 90 and 85, I need to get worried. So, anything 10 less than like 90 minus 70, 90 minus 80, 90 minus 60, I need not worry. So, whenever we do noise monitoring of machines, we have to ensure that the ambient or background noise is less than 10 dB. Is less by more, that is a better way of looking, less by more than 10 decibels. Okay. So, in a room, if I was to measure the noise radiated by a say overhead projector, the overhead projector makes 40 decibel. If the ambient noise level is 20 decibels or 25 decibels, I am okay. but then I can say that the projector made 40 decibel of noise. But if the ambient noise is 35 decibel and I would say the projector is making 40 decibel, it would be erroneous. So, always while you are doing noise monitoring, always it is good to measure the background noise level, and background noise level should be less by more than 10 decibels. Okay. So, always a check, and then there are certain ground rules, like when you do a noise monitoring, okay, the measurement is done by a sound level meter, which has a microphone and a built-in microprocessor circuitry, which gives the SPL in decibel. Now, the rule is, the convention is that this SLN should be always at a distance of about 1.2 meter from the ground. Okay. And again ensure that the background is less than 10 decibels. Okay. That is only one thing you have to take care of. And another important parameter which you have to report is, of course, the temperature, humidity and the wind speed, because these parameters may affect the speed of sound, because you will see the speed of sound is dependent on the temperature of propagation. In fact, at 20 degrees Celsius, speed of sound is 341 meters per second in air. Okay. This speed of sound in water is about 1500 meters per second in water. In steel, it is close to about 5000. With density, the speed of sound is also increasing. Okay. Something you have to keep in mind. Okay. And density of air is 1.2 kg per meter cube. Density of water is 1000 kg per meter cube. Density of steel 7800. Okay. So, certain values you have to keep in mind. Now, we have just discussed about the sound pressure level in terms of amplitude, but again our ear has been made by God. This sound is also a wave, so it has an amplitude and it also has a very important quantity, it is frequency. So, the human ear has an audible range which is from 20 hertz to 20,000 hertz. So, we can hear any sound which is in this band of 20 hertz to 20,000 hertz or 20 kilohertz. So, those which are above 20,000 hertz or 20 kilohertz are known as ultrasonic waves. Greater than 20 kilohertz, and infrasonic waves are less than 20 hertz. Okay. But again, like any other linear instrument, you would have seen the frequency response of an instrument. So, this is the amplitude ratio, output by input. Output by input will be 1 or 1 in log scale, which will be 0 decibel, because log of 1 is 1. So, this is typically the response of any instrument, and this happens to be its natural frequency. Okay. If you think of our human ear, unfortunately, God has made our human ear. Human ear is highly nonlinear. It is not, if it did behave like this, life would have been very easy for us. But the human's ear sensitivity is somewhat like this. Okay, and this is about 1000 hertz. I would say frequency response or sensitivity. Now, you may be wondering how did I generate such a waveform? Well, these are from in the early 1900s. People have done experiments with human subjects, and this is what they found out, that the human ear responds like this. So, we hear poorer at low frequencies and so on. Okay, and this is what is known as the so any instrument. Suppose I use this with measure this sound level with a microphone. Okay, I will superimpose, I will do this weighting function on this microphone measurement to give what is known as the human weighting. Okay. So, and these bands, this could be divided into octave bands. Okay, you know what octave bands are? Octave bands are those frequency bands where the F upper is nothing but twice of F lower. Okay, and the center frequency is √2 of okay. So, in every octave band such weightings corresponding to human ear is applied. Okay, if you go into the handbooks, you will see for every octave band where the weighting factor is, and this is known as the A weighting factor. Okay, so 63.5, 125, 250, 500, etc. Okay, for all these octave bands, you will see what the weighting factor is, but for 1000 hertz, this is about 0 and so on. So, there will be a subtraction. So, this weighting values are applied to the frequency spectrum obtained from the SPL, and then we can get what is known as the dBA or dBA. This means the A weighting. Because of human hearing, and this is measured at a 40 phone loudness level, and that corresponds to normal sound pressure. When the levels are high, for example, if you are talking about aircraft takeoffs, very large noise levels, you can there are also a C level and a B level, but the international convention has to be used the A weighting, and all if A weighting has been written, same 90 decibel could be 87 decibel dBA, because this means this has a significant low frequency levels. okay, low frequency signals are there. So, whenever A weighting is given, it means that it has been corrected to human hearing, because if I give a measured value without the A weighting, it may not relate well with our sense of hearing, because dB is what a microphone would have given me, but I would be perceiving dBA. So, this weighting factor has to be given, so that I get the correct sense of hearing or correct sense of the sound level which I have measured. Okay. Now, let us talk about the acoustical. So, for example, so if in noise monitoring I have to ensure what of equipment or machine, what are the things I have to report? One is the SPL level, either in dB or dBA. Next is the background level, dB or dBA. Very important is distance from the source. Number 4 is the ambient conditions, that is temperature, pressure, humidity, wind speed, of course, time of the day. Sketch of the machine or the layout. Okay. So, for every machine I could be doing such measurement for every machine and keep it on a record. Okay. And later on for diagnosis, sometimes we may do the sound, pressure, time history recording and store it with us. For example, we can still apply the techniques of FFT to get what is known as the noise spectrum. Now, the spectrum could be a narrow band spectrum, or what could be an octave band spectrum, or a 1/3 octave band spectrum. Okay. Now, this helps us diagnose the problem. For example, if you recall, I was talking about a machine. If this machine vibrates, this will be vibrating at a frequency f, and the particles obviously next to it will be also vibrating with the same frequencies. So, sometimes it may not be possible for us to, while doing diagnosis, to even go near this machine. It's not, machine may not be accessible. So, but at a remote location I could be just putting a microphone and then doing the narrow band spectrum, and then maybe I will find out the running speeds of these machines. So, noise monitoring also helps us to access machines remotely. Okay. Now, let us talk about the noise fields or sound fields. I had talked about a machine which is radiating in all directions. So, I draw with distance very near the machine, the 1 by r law may not be followed, and this is about half or this distance is what is known as the near field, and then the sound level may be a constant. So, I draw by this red line the sound level, and then what happened with distance, this is going to come down by 6 decibels, and then towards the if this is a boundary, now this level has happened. So, there are 3 distinct zones. So, this is the near field, and this is the free field, and this is the reverberant field. Here you will see drop by 6 dB double distance. And this is the distance r. Okay. And so, always a good area to measure, as I was telling you, is the free field measurements. So, in the noise monitoring you have to also, like when you say distance from the source, you can also say whether it is in free field or far field. So, always avoid near field and always avoid reverberant field. So, in a shop floor you can move your sound level meter or microphone away from the source and see whether this 6 dB decrease is there with doubling the distance, and whenever they try to increase, they are close to the walls in the reverberant field. Like you would have seen, if you go to the corner of a classroom and speak, because of the reflections in the wall, the sound pressure level will increase. Okay. And this is what we need to measure in. There are a few other terms associated with the sound pressure level or in noise monitoring. One is the sound power level, denoted by SWL, sound intensity level, SIL, okay, and the sound power level is nothing but the sound intensity level times the normal area. Okay. There are instruments to measure sound intensity level, and then knowing the area you can find out the sound power level. The advantage of using sound power level is sound power level of a machinery is not going to change with the environment. SWL will not change with the environment or field. So, when I label a product with a certain sound power level, it is going to be same whether it is in location A, location B, location C. So, it is very easy to characterize the machinery in terms of the sound power level. If something is wrong with the machine, its sound power level will change. Well, to measure sound power level, it is a little involved process. So, it may not very easy to measure the sound power level in situ at a location, but nevertheless there are methods of the sound intensity level by which we can measure the sound power level. But the sound pressure level, if we measure to monitor the health of a machine, we have to tell the field conditions, the distance from the source, and ensure that the background is less than the less by more than 10 decibels. Okay. Now, how much sound does human ear perceive? If a human ear was to sense 90 decibel and 91 decibel, it would not be able to do that. A human ear cannot distinguish less than 3 decibel. That's something you have to keep in mind. You would have done a noise control and brought down the level from 90 to 90 decibels, 92 to 90 decibels, you will not perceive it. Okay. To make a significant difference, it has to be more than 5 decibels. Okay. So, when we talk about alarms, sometimes a mere difference of 2-3 decibels will not be noticed by a human ear. Okay. So, we have to keep that in mind. So, sometimes during noise monitoring, there are machineries or there are online analyzers which will tell you the exact sound pressure level. So, sometimes numbers may guide us to give us the better feel of the machine's condition. So, to summarize in noise as I said right in the beginning is not used as a parameter per se to do condition monitoring of machines, but for the fact that they give us an indication that something is abnormal with the machine, we need to study noise and need to know how the background of the machinery's noise level can be measured, and the importance of A weighting, why the numbers of A weighting are there, and what is their frequency content. Okay. Thank you.